All right. What's up, everyone? Welcome to week 66 of Chill Kernel Hacking for Fun. I'll do my usual test in the chat. So this week is going to be very interesting because we are actually scarily close to the end of the MIT course. I've been doing this coursework every week for 66 weeks now, and I'm on the final lab, which is lab 6, and that's been this networking stuff that we've been doing. What's up, Fong? Welcome. Yeah, I've been doing this final lab 6, and last time we finished exercise 12. And I didn't realize this last week, but if we scroll down a little bit, there's some challenge exercises, but actually the only exercise left is exercise 13, which is some kind of web server thing. And that's it. That's the end of the course, basically. Technically, there is this lab 7 thing, but that's just the final project. And for the final projects, you could either do lab 6 or you could do your own projects. And for simplicity, I just chose to do lab 6. And so basically, yeah, when I finish lab 6, that will pretty much be the end. Of course, I can go and continue in whatever way I want. You know, there's a lot of other ideas here. But basically, yeah, basically we're pretty much done with the course as soon as we do exercise 13. We'll see how that goes today, but it might actually happen that we finish the coursework today, which would be pretty incredible. What's up, Krishna? Completed stream 2, refactoring build system. Nice, thanks for watching. You are really in the early streams. Personally, I don't know how valuable those are exactly. So if, in case you feel like jumping ahead, week 13 is the proper place to start, because that's when I actually start working on this coursework. Yeah, let me just quickly check in on the stream, make sure the audio is okay and everything. Seems like it. Test 1 2. All right. Yeah, so here's what we're going to do today. I'm going to kind of check in on my previous work from last week. I'm going to explain how I got it finally working. Because for most of last week's stream, I was really struggling to get the input data to be received from the network. And at the very last minute, I got it working, but we didn't have enough time to explain it fully. So I'm going to explain what went wrong there and how we fixed it. We'll take a look at some of these questions. Maybe, I don't know if I will do a challenge exercise. Maybe we will come back and do some of them. But then otherwise, I'll continue with exercise 13. Also, what's up, Kurt? All right, Fong, how can you share how you learned programming? I learned programming in general, first by kind of teaching myself it. I was writing some programs for my TI calculator, TI-83 graphing calculator, just to do some simple formulas in high school. I did a little bit of Python scripting there. Then I went to university and I studied computer engineering, so I learned some more about programming there. And then I've been working as a programmer for like 10 years. But as a general answer, I worked on a lot of personal projects to learn programming. I would say that was possibly even more helpful than a lot of the university stuff. What's up, Kurt? Okay, so hey bro, would you mind to say me how I can set up a GitHub project that has old versions of the software? I tried to run it, but IntelliJ gives me so many errors. I'm using Java, Maven, Spring Boot. I don't have any experience with any of those technologies, unfortunately. So yeah, I'm not going to be a great help with that, but maybe someone else here knows. But we're doing a bit more of like C programming here. So you might be best finding a Java community. All right, sick. So we got a bunch of people in the stream so far. Let's get into it. So first thing is I'm going to share my Git client. And let's just take a look at the state of our working tree, because I left it in a little bit of a messy place last time. Yeah, so this is actually an important hunk. These two are relevant. This was something I tried. Interesting. This is actually, I don't actually need this, I think. So maybe even before I do anything, let's just run the kernel and just make sure things are still working. So we run the kernel. Okay, what happened? Received page log. Yeah. Let me see. Page fault. Input. Yes, this is important. So I'm just going to quickly put .c. Just to show you all the state of the progress that I made last time. Okay, nice. So what are we seeing here? So basically this is working. The OS boots and it sends out an ARP request into the QEMU virtual network. And then that ARP request is received by the OS, which forwards it to a user space process, which prints out a hex dump of the data. And this is what the coursework says we should see. If we did things right, we should see this big hex dump, and it is the same hex dump. Oh, hi Bacon, welcome. Nice to see you. So that is the working state. So let's get into it. So I'm just going to clean up what the in progress part. There's a lot of debugging stuff that I don't need anymore, so I'm just going to delete those, delete these. Going to delete this, going to delete this. This is all some other debugging. This was actually needed. Okay, and then this stuff, I'm actually going to delete everything here. We don't need this hunk. We don't need this either. That was just a bit of an experiment when I was debugging. Technically, yes, this is important. This is also some more debugging. Yeah, we don't need this. Yeah, after I just clean this up, I'm going to explain how it works. I'm just going to switch over here now. So we have a bunch of commits here. We have this temp thing, which is not that important. So this, what I have staged right now, actually Oh, actually, I don't want I don't want that staged. I just want to delete this actually. So what I have staged right here, I will want to amend back into probably the initial RX commit, which sets up a lot of this stuff. I think if I do Control F, it'll automatically jump me there. And then I can do a, I will make a fix-up commit. So that's the fix-up commit that we just added right here. This stuff is all relevant for the RX, the receive commit, the function that adds, the commit that adds the receive function. I think, so we don't need this, we can delete that. So everything here is actually going to get deleted. We don't, this is all just purely for debugging. Purely for debugging. Actually, no, wait, so we have a function, this tx function. Whatever, well, I'll be a little bit sloppy with it, and we will include that also. Don't need this. Do this. What's up, Sandeep? How much work do you put to come up to making a kernel? So lengthy and hard, man. Definitely, it's super hard. It's a lot of work, and I am not even really trying to make a super production level kernel. I mean, I've been doing this OS course for a year now, and it's taken me like about 120 hours, 150 hours maybe, to do this. Yeah, I'm just doing little experiments. I'm intentionally not really. I'm just being realistic that I'm not going to be able to make a production level kernel just casually in my free time. Okay, so with this commit, so we have staged here. This is the thing I just staged. That's going to go into the impl basic receive commit. I'm going to do a fix up. So I'm just kind of preparing my commits and my Git history. We'll apply all these fix-ups later and make the history a bit nicer. So this stuff, okay, so this thing is completely, no, this thing, I just want this. So this hunk right here is completely separate. This is just a small little quality of life improvement. I don't know why I didn't do this a long time ago, but when the kernel page faults, it just prints out. Now it prints out the address that the kernel page faulted on. That's just a small quality of life improvement. Yo, man, what's up? What's up? Damn, I don't even understand. No worries. So good to have you here. Yeah, feel free to ask questions. I won't be able to answer absolutely everything, but I can try to do what I can. So this commit is just going to be something like print faulting adder on kernel page fault. So this one is actually important. This is going to get fixed up into here. Okay, and then actually, this is kind of important for the moment too. I'll get to that later. So this is all just purely debugging stuff. So let me just go. Still working. Okay, I think we're ready to delete some of the debugging output. Or maybe even at least just like stage it in case we want it again. But no, I'm just going to delete it. I'm a little bit undecided on that. I'm undecided because it can be useful to have access to like these debug logs, and so it would be kind of annoying if we needed that soon if I deleted it right now. I'm just going to stash it, and so we don't need this one. This is easy. This stuff is actually all totally unnecessary. So what I'm going to do is I'm going to stash my unstaged changes, debug prints. And then now if we go to our stashes, we can see that these hunks are nicely saved here, but they're out of our working tree, which is a bit cleaner now. And we can fix up into this commit. So now we have all our fix-ups commits, and now it's time to actually apply them. How do I add a tag? Tag commit T123, just in case something doesn't work here. And I'm just going to fix up all commits with capital S in the maybe just above the current commit. Yeah, I'm going to apply the fix-up commits above the selected commit. That was fast. Okay. So now this is what our history looks like. And let's just run the kernel again just to make sure nothing broke in the meantime, but hopefully it didn't. Okay, good. We're still working. Yo, what's up, MXD? This is not kernel hacking, just you developing a common LKM clickbait, lol. I think you were in another stream. Nice to see you again. Yeah, I mean, I'm actually not developing a Linux kernel module, but it's totally true that I didn't write a lot of the OS from scratch. But it's not Linux. It's a custom OS. Yeah, but totally fair if you want to critique me for not writing everything from scratch, because I totally didn't write everything from scratch. Okay, so now that our history is a little bit cleaned up, I will even reorder some stuff. Yeah, so initial, I can even take the time to rename some of this stuff. So this is no longer a whip commit anymore. This is actually what does the commit even do? This is okay. It's a little bit messy, but that's not really that important. So let's explain how this works. Right, so what we're seeing here that the OS received some data from the network. So the general flow of what happens here is that, so first, so during the boot process, we initialize the NIC, and we call this function E1000 init. And that does all of the necessary initialization for the transmit and the receive sides. We set a bunch of memory mapped IO registers to be in the correct state. We set a bunch of registers to point to a transmit ring buffer. And then we also set the head and tail pointers in that buffer. It's pretty much very similar on the receive side. We have a receive transmit queue, a ring buffer, and we also initialize the memory mapped IO registers to point at the head and tail of this. Sorry, we have the ring buffer. We point some registers actually at the address of the ring buffer. That's this RDB thing. And we initialize a length register, and then also a head and tail registers, which contain indexes into this. So basically, all that just kind of brings up the NIC. What happens next is user space runs. And if we go to init.c, so we're running this program called test init. Test input. Yeah, I see a bit of a discussion going on about the meaning of hacking. Yeah, I mean, it's there's different meanings of the word. I'm kind of inspired by one of my favorite YouTubers, Andreas Kling, and I kind of shaped a lot of my content around that. And he calls himself doing browser hacking and stuff like this. And I think there's also a bit of kernel hacking somewhere in there too. So that's just a bit of the terminology that I'm using. Right. Okay. So we're running this program called test input. And that is run as the init process. Test input looks like this. It does two things. It forks an output helper process and also an input helper process. And announce. Yeah, that's just kind of the architecture of what's needed here. And once those are both set up, it runs this function called announce, which sends an ARP request. And the way it sends an ARP request is it sends an IPC message to the output helper environment. That's this helper process that was forked right here. And if we look at I need to be in the right place. If you look at the Wireshark capture, we can actually see these requests being sent out. So here, this first packet is the ARP request being sent out by the OS due to this function. And then the process kind of spins, and it receives. It's spinning, receiving for IPC messages. Specifically, it's waiting for IPC messages from the input helper process, and that's the one that we've been working on. The input helper process is, the process is forked from the original one, and then it runs this function which just spins in a loop, and it calls the system call we added, which asks for data from the driver. And it just spins it in a loop, trying to receive data from the OS. And if it ever gets data, then it uses an IPC message to send it to the input. Wait a sec. Let's go back to the diagram. There was this whole architectural diagram. Right. Yeah, the input helper receives data from the OS and then passes it forward via an IPC message to, to someone. In this case, it is going just to be the parent process that called us. And so basically the input helper is just when it gets some data, it sends it back to the parent. And the parent is going to be sitting here waiting to receive the data. And when it gets the data, it just hex dumps it, and that's it. So that's the general flow of how things work. And we were stuck for a very long time because of this very kind of odd thing here. So what I learned is that this line is actually necessary. If we try to run things without that line, then it doesn't work. The kernel kind of crashes. And the kernel crashes when the data comes back in. And specifically the kernel, through a lot of debugging, we found that the kernel was crashing right here. So let's talk about this. This is the function in the driver that, so it's basically when user space calls the sys network receive system call, it basically just calls this driver function, which tries to read one entry out of the receive ring buffer. And then if it can do that, it copies it into a buffer, into the buffer that user space passed in. And what we were seeing is that this was crashing. On the first write to the buffer, we page fault. And the reason we page fault is because this test input function, so this is the parent function, parent process. It is forking helper processes. And the key thing that I forgot is that when we do fork, we have copy on write in the OS, which means that the child which is running this function, basically its entire address space is marked unwritable because we want to page fault if on writes, basically, to writable pages. And that's what happens here. So we fork a child. The child process kind of gets like frozen and marked unwritable. And then we pass a pointer. So basically the way this flows, we have this memory allocation in the child process, and we pass a pointer to it, which the kernel is supposed to write into. But since the child is copy on write, doing this write triggers the page fault. So in order to kind of hack around that, what I tried doing is just doing kind of a dummy write to that allocation, which triggers a page fault and actually pages in a copy of this buffer for us. And then now if we do that, the kernel no longer page faults when it receives the data and tries to write it back. It's able to actually write the data. What's up, Saksham, and also Afna? What's up, dude? Nice to see you. So that's just explaining a bit of how this works. There's kind of an important question here though, but this is not really ideal. It's kind of yucky that user space needs to intentionally make sure that the buffer that it passes to the kernel is like paged in and everything. It would be kind of nice to not require this. I wonder if we can fix this in a reasonable amount of time. I'm going to close down some of these. I'm just going to close down a bunch of these things. Okay, 1,000. So what could we do to help this situation? We could, ideally, the kernel wouldn't be so fragile. If the kernel tried to write to the memory, it would ideally handle this. And I guess just to sketch my thinking, there's some different ways we could do this. C6, and we are on May 4th. So here's the problem. Kernel is very fragile. Requires that all buffers, all memory passed to it will not page fault. And so what can we do? One idea is the kernel can test the buffers before writing, or the kernel can simply handle the page fault. So right now we have a panic here. Handle page fault handler. When the interrupt comes in, we so in the Twitch chat, what's up, Sakam? Oh, maybe same side. Okay, someone's in the Twitch chat also. I still don't have a good solution for seeing both chats. Okay, but currently we just do kind of something very simple, and if a page fault exception happens, we just panic. And I wonder if there's something else we could do here. For example, we could handle the page fault and just return back to the kernel thread that caused the page fault. That's kind of what it would look like. Just return to the kernel task that caused it. The tricky thing here, though, is actually in this OS setup, all of the page fault handling, it happens in user space, which is a little bit odd, but that's the design of this OS. So actually the code for, I don't even know. I don't actually even know where cow, if I search for cow, fork.c. The code for handling a page fault runs in user space. So maybe what would happen is that under some special conditions, we could possibly allow execution to keep going and actually enter user space again to fault the memory back in. but then it needs to return. Yeah, this like, yeah, I don't know exactly how this would work, because under normal circumstances, user space is triggering a page fault, which triggers the CPU exception, which then comes into here, which then sets things up, and then passes control back to user space to handle the page fault. Set page fault handler. I'm forgetting how the return actually happens. So this is the page fault handler. But then what happens? Maybe we need to go to the page fault assembly. TF entry. I think it doesn't go back. I think it doesn't re-enter the kernel. The page fault happens. It's kind of a minimal amount of setup is done, and then it transitions back into user space to call the page fault handler, and that's what happens here. We do it, and then everything that happens here is just to return execution back to the original user space execution flow. So I think it would be super hard. I think it would be really hard to somehow reuse this from within the kernel. I'm just going to write that down. But our page fault handler actually runs in user space. It's designed to page fault in faults that originate from user space. Kernel handles the exception, and then with a thin layer that just delegates, like directs execution back to a user space page fault handler, which does everything, including returning back to the original execution flow. Yeah. All right. Yeah, what's up? Ironic. We are working on. We are thinking about this like part of the kernel where we like receive data from the network, and it involves this code here, which is like looping and passing a buffer to the OS, which the OS should fill. And the problem is that the OS is super fragile and it was page faulting unless we poke the memory before passing it to the kernel. I think this is pretty challenging. How would we reuse this from the kernel? It would be super weird. So kernel triggers a page fault. Then it would direct to user space fault handler, which would then need to return back to the kernel somehow. But this, like, there's so many ways this would not work. Because problems. One problem is that when kernel is entered from user space, the kernel stack is reset. And so that's a problem because we're trying to return back to kernel execution, but that means we need to like preserve the stack that it was running on so we can return back into it. But currently there's just one kernel stack. And if the kernel was running, triggered a page fault, delegated to user space, there's no way to return back to that original kernel execution at the moment. So that's a huge problem. So basically option 2 is very difficult at the moment. At least, oops. Oh, sorry. Oh man. So that was one kind of exploration. How to do this. Another sub option for option 2, simply re-implement the page fault handler, but in the kernel. That probably makes a lot more sense. And maybe it's not even that hard, but that would be a bit of a project. I'm more interested in this option number 1, maybe. Can the kernel test the buffers before writing? And actually, maybe we're even missing something. Maybe we are missing some asserts, network receive. I actually do have the user mem, but my permissions were wrong. I'm missing the PTE write. Let's try this one more time. Now that I added this permissions check here. So this function call is the first thing that happens when we enter this syscall, and its goal is to validate the passed in user space memory to make sure it's appropriate. And I guess I actually had a bug. I was not checking that this buffer should be writable. So now I would expect that we would get like this kernel assert. Oh, okay, here we go. User memcheck assertion failure. And then it kills the process. So yeah. But an even better, I don't actually know what the other solutions would be. Fundamentally, we need to page in the memory if we want to make the kernel less fragile. There needs to be some way to page in the memory. The only way we have to do that right now is in user space, and we can't easily reuse that without a lot of modifications. And so probably implementing a separate like copy of that code within the kernel would be the most straightforward solution. which would be interesting, but that's a little bit of a divergence that I don't want to quite get into right now. So for the moment, I'm just going to poke the memory to page it in. Otherwise, the kernel faults when it tries to write. Ideally, the kernel would be able to fault it in itself. Okay. So that's actually important. I'm going to amend this into here, and then this is also going to be amended into here. And then here were just a few things. So let's see how we're doing. Also, I feel like it's a good time to take a quick palm tree break. Make sure to stand up and stretch and whatever. I'll be right back. Okay. Okay, so now we can, okay, I was having a lot of trouble getting these grading scripts to work. Maybe I will briefly try this, but I spent a lot of time on it previously, and I'm not sure it's worth the effort. So that's test output. Test input. So there's some kind of issue here, but I don't know if it's an issue with my code or the testing infrastructure. Let's just quickly take a look. So this is in test input 5 packets. How does this test even work? So it makes a thread that sends some UDP sockets. No, send some UDP packets to this IP address. And then what? It runs the test input program. What's up, Digitalized? Nice to see you, dude. I am spending a little time trying to understand this testing infrastructure because I'm currently failing it, but I don't know if it's like from my code or like these scripts are like very old. Joins the thread. and then it parses the QEMU output. And then it parses the PCAP. Ooh. Okay, yeah, I don't know. But apparently, actually, we can just test input. This thing spins here in a loop, receiving stuff. So we could, and even, so it seems like we can even send stuff externally to it. But what I kind of don't get is this. I think, what IP address do I need to use to connect to this is like kind of going back quite a while, I think. Yeah. What? Yeah, so here's how this. Maybe I'll ask ChatGPT. I have a QEMU guest using a virtual network. Can I ping it from the host machine, or how to send a simple UDP datagram to it from the CLI? Oh, but there's this port forwarding thing, right? Okay, I'm just going to YOLO a little bit and try this. So let's run the OS. Now it's supposedly sitting there in a loop, waiting to receive data. And man, I sort of wish I knew print. Yeah, kind of. Which ports? Make which ports? Port. Had to learn how Android tools work to remove a family member virus from their phone this morning. Ouch. Ooh, bummer. I'm just gonna do this. Run echo serve. Let's just try that. Does this work? What does echo serve do? Okay, this thing actually makes a real echo server. And it is using all these networking APIs that come from lightweight IP, I think. Okay, interesting. Let's see. And make NC7. NC7? Oh. Well, that asserted. Bam. Match. Okay. Interesting. I think these lines come from Kimu. So yeah, that did not seem to go very well. What did we assert? 247. Wait, what am I doing? 1,000. 247. So in our receive function, we're asserting that the tail descriptor should always not have the DD bit. Let me disable that. I'm just gonna see what happens if I just comment that out. Okay. One more time. And I think the reason maybe that failed actually, we never actually reset the descriptor. Actually, no, we do. Okay, whatever. Hello? Okay, nothing seems to be happening. Okay, so it seems like this is not actually working that well. Some more. Every line you type should be echoed back by the server. And what do we actually see happening? Pretty much nothing, except for these messages that regularly come in. Okay, so seems like we have some improvement we could do. Okay, so maybe it's actually important. There's no way to test packet receiving. Put test of make grade. Let's go back here. Let's at least just see the pcap that was generated. So let's run this. So there's no qemu.pcap. We run the test program and it's going to fail. It takes kind of a long time. Or maybe is it not failing anymore because it's hanging because I removed this assertion. Okay, maybe so let's take a look at this pcap. And it has two things in it. The request and the reply. And we're expecting a bit more, apparently. I think the problem is that something like, I don't know if we can connect to it this way. It's connecting to localhost. Okay. I sort of think the problem is not in the kernel code. It's somehow in just being able to connect to the QEMU guest. Yeah, I don't know that this would work. So time to return to ChatGPT. This stuff is my worry for this lab since I run them in Docker containers. I will probably have these ripped on Docker docs. Well, yeah, for you, I think this stuff should be more well supported since you're using a more recent version of the class. Can forward specific ports from host to guest. So that's kind of what I was, wait, okay, that's the deal here. That's why it's using localhost in the test, because there's this port forwarding. Okay. I'm going to add back a bit of logging here. cprintf received a buffer. I'm just going to run this thing actually. So I think we should be seeing more of these unicast match lines when things go through. Let's see localhost. Let me try a more simple approach. So UDP and TCP, port 7 and port 80. What if I just hard coded? Actually, also netcat-u. I think I want to try using UDP. So what I'm going to do, this port 7 thing is like kind of weird. I'm just going to change it to something 2, 3, 4, 5, I don't know. Okay, palm tree break. Be right back in 20 seconds. Okay, let me run this again. So now let's do this. Something like this. Echo test. Does this work? Okay, things are kind of hung. But we were definitely able to receive one buffer. So I think this is being called a lot, just to confirm it. I think this is being called very, very often. Yeah, it's being called constantly in a loop by user space. I'm just quickly rereading this code to see if I can find any possible issues. So we get the tail pointer and we get the descriptor after it, or the index of that by doing a modulus with the number of args descriptors, which would be 128. It's actually very interesting that this thing asserted previously. But then we basically just we look up the next descriptor. And we are looking to see if it has any data or not. And so far, we're not seeing anything. this whole thing kind of arrives in a big clump. Yeah. And there's this unicast match thing. Post forward. It says you can use port forwarding to forward specific hosts, specific ports from host against. I'm just going to ask it. How would I use netcat to do a basic UDP packet send here? Right, so we're in theory sending data to port 12345 on my host system, which is a Mac computer. Kimu is going to listen on that. Kimu is going to start a server that listens on this port on the computer and then translates it into accessing port 7. UDP port 7 on the guest. The details actually of the port number don't really even matter. All I'm looking for is to see that anything is received at all. And we get one message with this ARP response. That comes internally from the Kimu virtual network. It's kind of a different thing to send something. What is W1? Optional helps. Hello guest. Yeah, I think. So what's interesting is we actually do see some input. Well, some log message, like some stuff happens. Huh. Maybe it's time to open up Kimu again. Bam match. How is that possible? Is broadcast ether address? So maybe that's why we this thing gets printed in response to this line, I believe, the ucast match. But we seem to be falling into the broadcast match, and actually, maybe the reason is that actually in the OS I am allowing broadcast, and I don't know if I needed to do that. I think I actually didn't need to do that, and I think that could be causing the problem here. Let's try this one more time. So we have our normal receive from the ARP response. Okay, this is interesting. This is different. So now it says there's a mismatch. An exact mismatch. And so that means, I believe what that means is the Ethernet address being sent doesn't match the one of the host, and so it's rejected by the NIC. Let's see, run test input. I'm just going to remove the PCAP again to clear it out. We'll do this, and let's do 2 of these. 1, 2. We'll stop execution, and we'll open up the Wireshark, which only has 2 things in it. But this is interesting. It gives us a bit more information about what is going on here. We still see is broadcast, actually. Does Netcat send UDP broad? Are these when Netcat with these Netcat commands, does it send Ethernet broadcast frames? Broadcast packets are 25, 25, 25, 25, which is actually, wait, 255, which is this FF thing, actually. But QEMU internally must create an Ethernet frame to send to the guest OS, and that Ethernet frame must have a MAC address. It appears the address is a broadcast adder. How many is it? It's like 6. Which is being rejected by my NIC because it doesn't match the ETH address of the guest. Solutions enable promiscuous mode in the guest. Sheesh. This is tricky. So what do we know? We know that I'm just gonna okay. Netcatting data, so the grade 6 script fails. Only the 2 ARP packets are seen. Are seen in the PCAP. The grading script tries to send data from the host to localhost. To localhost using some port on localhost, which QEMU is supposed to be forwarding. It seems like QEMU is rejecting the. It seems like the NIC is rejecting these packets because they don't match the address. So there's one possibility we can try, which comes to mind. I don't actually know how well this works, but we can add the FFFF thing as a secondary address. I believe this RA thing, it can store multiple of these, I believe. Let me see if I have a screenshot of where that was documented. Receive address low. 16 registers containing the, like there's RAL. Yeah. The addresses stored are used for unicast, multicast address filtering. So this is kind of a guess, but I am just going to try adding the broadcast address. Actually, I don't even really understand this. The broadcast Ethernet adder. Okay, special MAC address used to indicate that the frame should be delivered to all devices. Okay. I don't know. Let's just try this. So I believe I've added the broadcast address as a second valid address. And check it out. It matched now. But we didn't actually get a hex dump. And why didn't we? The PCAP still has nothing in it, which is kind of frustrating. But it's interesting that that kind of worked. So it seems like it added this broadcast address to this list of allowed addresses. And then it didn't get, I don't know, immediately rejected like it was here with the inexact mismatch, but nothing really happens. I am expecting a little bit more here, so it would really be here, received buffer. All right, time for another palm tree bake. Be back in 20 seconds. Okay, it's tricky, so check the chat. Cat Flare, what is up? Hey yo. And also, what's up, Useless? You should check out LeMine one day. They do a lot of heavy lifting for people new to OSF. Nice. Yeah, I actually am very curious about that. I know they make it a lot easier for the boot process in particular. Yeah, I think actually once I start my own OS, I might use LeMine. It seems more modern than Grub. And I don't really know if I want, like, I don't think I want to keep using a custom bootloader like I'm using currently. What's up, Vice? Okay, this is really interesting. It seems like clearly we never clearly user space never is receiving a buffer. So I just wonder, is there something I could be doing wrong here? Basically what's always happening is this no data thing, this no data code path is running. It's like never has any data. Even if we do this UDP stuff. That's very noisy, so I'm going to remove that. But even when we do this UDP thing, this netcat UDP thing, which is actually matching the filter somehow. For some reason, there's no data actually being provided to the receive ring buffer. I'm going to re-enable this assert, though. I think that might be a bit of a clue, actually, because that was kind of weird. So maybe it's a clue that something bad happens when I connect this netcat thing, actually. That might be a clue that something is going wrong. At least it's a clue that my expectations are kind of... I also... It's very annoying that this receive thing is called super often, and I think the only way I know how to slow this down, I don't know how to, we don't have any sleeping in the OS yet. I can't put a process to sleep, So maybe what I just can do is add a long ass loop. Wait. I'll just put it right here. Int I equals 0, I less than, I don't know, 5. Let's do like 500,000. I don't know. This is totally random. So I'm just wondering, does this slow things down? Because it's super hot right now. Maybe this is even being optimized. Okay, that's a bit more reasonable, I think. I want it to be like once per second, something nice and easy like that. I think that actually is improving things. I'll do like 15. This is like the worst sleep ever. Okay, that's even still too fast. I'll do 25. Okay, I'll do 50. Okay, good. No, I'll do it even slower. I want it to be really slow. So the main issue is that I'm trying to send in data from my host computer, actually, like my dev computer, into the OS and have it be received by the network card, because that's actually how these grading scripts work. And I kind of wanted to run the grading script just to really make sure things were working well. But the OS can't receive data that I'm like piping into it from the outside. And I don't know, like why. So that's what I'm trying to figure out. And I'm doing this kind of stupid way of like slowing down of, instead of sleeping, I'm just incrementing an integer like a million billion times. Because currently, to receive data, we just like spam and like ask for it like in like a hot loop, which makes it kind of hard to debug things. So now I'm even going to go even slower than this. So then we send some data. Okay, so now we're in a bit more of a reasonable place, because I want to print out tail. And tail next. I have like a bad feeling about some of this stuff. So let's see what these variables are. So what happened here? Yeah, yo, Kazetsu, what is up, my guy? Great to see you. Yeah, also Lazy Git Enjoyer for sure. Yeah, gotta be one of my favorite Git clients. Yeah, hope you're well and doing well, dude. So what did we see happen? So tail is initialized to 127, which is the last descriptor. And then it computes 0 correctly, so that's good. And then now it's waiting for packets. And this seems right. Tail is at 0. So now let's see. So yeah, I didn't really do the critical part. Now let's see what happens when I actually send some data. Interesting. So all of a sudden the assertion, wait a sec, okay. Maybe, I'm gonna go back to my diagram. Okay, where's the handy buffer diagram? Could you try a single if the QEMU CPU is multi-core? Pretty sure I'm running it in single core mode right now. So yeah, I don't think we should have any issues with multi-core or threading. So something kind of interesting is happening. So here is how we initialize the ring buffer. Let me double check that. We loop through every descriptor and we assign the buffer pointer address, which is like this arrow, and then we clear out the status bit. Specifically, all these DD bits should be completely cleared out. Right, but it seems like what happened here is as soon as we got we tried to send data and then the assert fails because tail descript now has a DD bit set, which we thought would never happen? Question mark, question mark. Yeah, this is interesting. Oh, wait. All right, cool. Yo, we have a lot of people in the chat, 37 viewers. Welcome. Yeah, I'm debugging some network interface card driver stuff right now. What's up, Christian? Oh, Mark, what's your end game on this kernel stuff? My end game is I want to make my own OS that is super small and minimal and is kind of like a playground for me to do just like some experiments. Yeah, like explore features of x86, for example, or make kind of odd or weird OSs just for fun. I would say that's kind of my end game. My end game is not to like make a production OS that's going to take over the world or something. Very clearly not the goal. I don't even really care that much about also like having a desktop environment, really. I'm not super motivated by that. So I'm more just interested in having like a little playground to work on. Okay, thanks for the question. And I think I can get there. I've learned a lot in the last year of doing this, and eventually I will be able to start on my own. Yeah, a bit more of a learning experience. I mean, ideally, I'd like to be able to make some cool OSs using like this like playground, like this. I also kind of think about it in terms of like a set of libraries that I can use to like construct OSs easily. That's kind of interesting to me. Yeah, but I mean, yeah, learning is really the biggest part of this. I'm just interested in furthering my learning. And yeah, been getting pretty far into it. I think we're pretty close to finding this bug, guys. I think there is something maybe fairly simple, but this is actually huge. This debugging we've done, we can now see that so basically if we go back to our visualization of how the receive ring buffer works, it's initialized like this. T2, I think I've kind of heard about, there's like this other like YouTuber guy, but if I understand correctly, I think it's Linux based. But actually I don't know much about it. So head and tail point here. Head, and that's what we saw here in these logs. Tail is originally 127. And tail next points over here. I guess I'll illustrate that with this. And we actually did manage to receive one buffer, and then tail got pointed at here, and tail next was pointing here. Wait, let's slow down 1 second. So the way this works, so what happened here? Tail next, tail 0, received a buffer. So one buffer came in here and was marked available. And so that means when tail next was looking at it, which is how the driver works, we get tail next, and we check tail next and see if it has the DD bit set. And if it doesn't, we just return early. But if it does have the DD bit set, we proceed. And so that's what was going on here. And so the data, blah, 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 blah. And then it's like not a lot of stuff happens here. We clear out the descriptor. So we clear it out to make it look empty. And then we advance the tail. So we make the tail point here. And then we like exit. No, not no distractions at all. Okay, custom. Yeah, that's interesting. But yeah, it's like Linux based. Yeah, appreciate. Thanks. So now the thing looks like this. Tail and tail next is pointing here. We send in some data, but then we crash and assert on 253. Which it's asserting that tail never points to a buffer that has the DD bit, because my thinking was that yeah, my thinking was that the DD bit would be over like here. Bring this to the front. Like, because, so the next thing that's gonna happen is head's gonna advance one more and it's gonna place the DD bit here. That's my whole understanding of how this works. And it's possible I don't understand something correctly, because what this assertion means is that a DD bit is appearing here. actually. I'm going to try something which I think you're technically not allowed to do this, but I'm going to read the head. Head. I'm going to read the head pointer and just see what that looks like. You're not supposed to do this technically because, like, in production, apparently it's racy to read the head pointer. Okay. And then what happens here? That's weird. Head, was that? Nothing changed at all. The only thing, it seems like the only thing that changed was a DD bit got set here underneath tail, weirdly. Even though head is pointing at 1. Not like the states of all of the head and tail like didn't even change. Super weird. So it seems like randomly data got written here, which I don't think should happen. So now I want to see what the data actually is. Yeah. So I'm going to turn this into an if. If, then I'm going to, I don't know, panic. 1, 2, 3. But I want to see if we happen to have the DD bit set on the directly on the tail. I want to see what data is there, and I suppose I can just do that. I really wish I had a hex dump function. Do I? I do. I do have a hex dump function. Great. So I want to hex dump right here. So it's going to be kadder tail desc p buffer fizz adder hex dump. And what do I pass in? I pass in pointer and I don't know. Let's dump I don't know, 32 bytes and then panic. What's up? Junaidal Islam Jarif. Hi, any advice for this marathon? Good luck. Thanks. If you're talking about just me showing up here every week, I think my main advice is to keep it. And if you're interested in doing something similar, my advice would be to keep it manageable for yourself. Like for me, weekly is a fairly manageable thing. Other streamers stream way more than me, and I would not be able to keep up that pace. And so I'm going at a pretty slow pace that's just manageable for me to do over a long period of time. So that's been super helpful. It's also been very helpful to have this coursework, which just is like a set of tasks I can just show up and do. I don't have to do very much preparation for it also. So I think that's been kind of key parts of how I've been able to do this. Okay, so we're in our steady state. And yeah, this is looking kind of suspicious. Also, what? Why are there all these F's here? Because it is like an entire Ethernet frame, I guess. Yeah. We received the entire Ethernet frame. So how does this hex dump work then? What are they doing? No, I need test input. Plugin for Vim motions in VS Code. I'm just using the normal Vim extension. I think it's called VS Code Vim. But I have some of the plugins enabled, like Sneak, Vim Sneak. Yeah, I have some of these things enabled, like Vim Sneak and some other stuff. Although I don't use that super often. I'm using the normal Vim motions. This is really interesting. Something is kind of odd here, actually. So many things are actually odd about this. So we're dumping the buffer, and it actually seems like I'm actually going to copy over this whole thing. The buffer that's here, so basically a DD randomly appeared here underneath the tail, which should not happen. And when we go to look at the data that's in here, I was kind of expecting to see some of this UDP hello guest stuff. And that's not what we see. Wait a sec. 50. What I believe we're seeing is just the remnants of the older data that was originally there. Maybe we can double check on that quickly. But how does this look? All right, palm tree break. Be back in 20 seconds. Okay. So we have a bunch of data here. What I actually am going to do also, I'm going to hex dump directly in the driver when we do this mem copy. Hex dump this, just so we can really see the data that we are passing through. You know what, we could also, over here, I want to see some more details, like if we actually have the DD bit, I want to see the buff length. Buffer length. let's check this out. So here we have the legitimate packet, and then I'm going to send my like crashing one. And let's see what happened here. So okay, this is interesting. Ah, wait a second. Yeah, okay, that makes sense. So, oh, did I reorder these? Oops, no. So, okay, this is making more sense now. Okay, so a few things happened there. Here is the original hex dump for the ARP response that we received. Here is the data for this mysterious second thing that came in response to this netcat thing we did. And so the first things first, they're different. I didn't know that originally. I was having trouble parsing this. I was kind of thinking that there's this like header or something like that, but so these things are actually different. So that means when we send in data from outside, thanks for whoever's given some hearts in the chat. Yeah, that means data is actually coming in, and we are, I don't know, we're not handling it correctly, it seems. But the way the data is coming in is very strange. It seems like, so this is the state of the ring buffer. Head points here, tail points here. That's what we see from these prints. Head 1, tail 0. We even see even earlier, head is 0, tails 1.7 for some time. Then we receive something and head becomes 1, which means something got pushed at, like written at 0. And then during this cycle, we consume that data received the buffer. And then we advance tail to now point to 0. And that's the steady state for some time. Then another packet comes in. And what is so interesting about this, so in this situation, after we get these Kimu prints about the match and stuff like this, head is incremented. We see a change in state from the previous messages. What's interesting is we don't see that here. Head weirdly, strangely, is remaining at 1. And yeah, I'm going to do print out the actual buffer length. I kind of expect that when we see this hex dump, we're going to see this hello guest text that I'm sending. Oops, okay. and then bam. Okay, I don't see it. What does it look like? It's, yeah, no, this is what that kind of thing looks like. And we are not seeing any of that. Hey, Michal, just jumped. It seems like you are not receiving the data in the driver. And looking at your Wireshark trace, your hello guest doesn't seem transferred, but trigger your kernel driver. Yeah. Yeah. I think you're right. Yeah, the hello guest is definitely... It's definitely not here. It's... Something is, yeah, off. Something is, I mean, I'm sort of getting a better understanding of what's off, but yeah. You are not receiving the data in the driver. Looking at your Wireshark trace, your hello guest doesn't seem transferred, but trigger your kernel driver. It's off by one at reading or something like this. You know, I'm going to move the panic a little bit. Actually, what I want to do is kind of the same thing. I'm very curious. RDH and RDT, so I'm pretty sure those are the correct registers. What I want to do here, though, is actually kind of just the exact same thing. For the next one, though. If tail next desk. Next has data. 2. And then I want to just do kind of a similar thing over here. So what I'm trying to see is, I'm just trying to understand what happened. Like, it seems, so my understanding of what would happen, what should happen is in this state, which is what we were seeing where head is 1 and tail is 0. I'm expecting data to come in here, right? And then tail next points here. What we're seeing instead is that data is coming in here. And I actually have an idea, and it kind of makes me recall something. Okay. In the coursework, it was warning us that so this is actually for the transmit ring, but that this thing is an index into the transmit descriptor array, not a byte offset. Okay. So I just wanted to double check this because here we are using indexes, and I wasn't sure if it should be a byte array, for example, or a byte offset, but we're using indexes, and I think that should be correct. Yeah, okay. So now what I'm trying to see is like, what's the state of this thing over here? Is it possible that data was also passed in here? So that's why I'm adding these new prints about the tail next. Let's run it. So we have our steady state, and then bam, panic. And it seems like no. It seems like no. Tail next, it does not have the DD bit. And it's just seriously so odd. Like, what data is this even? We got a 60 byte piece of data, which doesn't look anything like hello guest. This is crazy. Yeah, what have we learned? So somehow a broadcast packet, first of all, is being sent. That's what we can see from all these FFFs. We know that because, I don't know, Ethernet. Is something a second ARB message? I don't think it's related to ARP, because it happens reliably in response to my netcat command. The ARP is just fully received here, I think. It's like this big hex 30 thing. Destination source. Destination source. '52 55A22. That's weird because this 22 thing. Wait a sec. Yeah, okay. So in the actual bytes first, but yeah, the source is the second thing. It's this 22 thing, which is the MAC address of the VM, which I feel like that doesn't make any sense. Or not, wait a sec, what? So in the first packet, it source is from the VM going out to the world, right? In this ARP message, it's coming from the ARP server or something to the VM, right? Going out to this thing, going to the VM. The 56 is the VM. Why did I do this? And so it seems like yeah, I'm really struggling to understand this. It seems like this packet, which happens in response to this netcat command, is sending data to the ARP server. And I have no idea, like, that's what it looks like to me, because we dump the packet that we receive, and wait, sorry, I'm so confused. The destination is the first thing, right? And then the source is the second. The destination is broadcast, and the source is the ARP server. So Michal, maybe you're right. Maybe it is ARP related. What's the program you're using to check the packets? This is called Wireshark. It'd be that the two messages are mixed together. All right, I think it's time to cheat and look at another OS. It's like we're getting just into too strange territory. So I have XV6 from 2022. Fuck, but I don't have a complete implementation. Dang. I mean, I could also look in other places. I could look in other places. I was really hoping to not have to do this. RX descriptors, yeah. Is it already time for another break? Wow, okay. Stand up and stretch. Be right back. Okay. Wow. This is interesting, so I will continue a little bit longer. Could it be that the two messages are mixed together? Let's just observe some more. What can we observe here? What if I mess up the port number? What if I send to like a you know, it's like a weird port that doesn't exist? Okay, so nothing happened. So it's very, very obvious that this weird situation where it was formally asserting happens directly in response to my netcat. And what does netcat-u do again? Oh, I should use verbose mode on netcat. Okay. That did not really reveal very much. Connection, but connection succeeded. If I give it like a... Oh, wait, what the fuck? I think there are other services running on the port. Or maybe not. Okay, let's go back to what GNU makefile. So I was doing a bit of a hacking and made it this, but let's remove this. Let's let's go back to this port 7 variable. Okay, so wait, so GDB port, it's like, maybe head and tail are not advancing. Okay. Maybe you should check the address where things are copied. Where things are copied. Yeah. Maybe head and tail are not advancing correctly. Yeah. I just had this weird feeling that my variables here are kind of messed up somehow. Like I had this weird feeling like I'm using a port that's already in use by someone else, but I think that would cause some kind of well, what about the other way? 5, 4, 3, 2, 1. UDP, right? Five, 4, 3, 2, 1. Bam, that thing, same thing happens. But now this is interesting. 4 more packets like came in. We didn't receive them because we like had panicked, but let's try that one more time. There's nothing going on. Let me send it to the wrong place even. Nothing happens there. But 5, 4, 3, 2, 1 triggers us. And look at this. It's like bam, 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 bam. These 4 other things came in. And we were not there to receive it because we like sort of immediately crashed. I think 4 more. So yeah, some weird ARP thing happened. And like for some reason the netcat thing triggers an ARP request. Yeah, so I feel like, so doing that triggers a bunch of stuff. And what could we do about this? We could just not panic, I don't know. Like, I don't even really want to, So user space is driving this by continually calling receive. I have another kind of extreme idea. I just want to do a basic loop that just loops over everything and sees which one has the DD bit set. Also, one thing I want to do is really radically reduce the number of RX descriptors. Like 128 is kind of an unwieldy number to use. I want to use something like 8, for example, just to make it easier. The reason I'm using 128 is just because the coursework said to do so. But okay, and then bam. Okay, something odd is happening. What's up, Siren? I'm in the middle of some really like low level network interface card debugging for this network driver. Okay. Here's what I'm gonna do. We're gonna really get hacky here. I am just going to, I want to make sure that user space continues to drive this and call us. User space is right here, and it just input. It does this big loop in case the return is -2 or 0. So here's what I'm going to do. I'm just gonna sketch kind of a new place. On every like tick of this thing, I'm just always going to return that there was nothing, just to make sure we keep getting invoked. And I'm just going to print out the state of the head and tail every tick as just every tick. And we're just going to observe how they change. What we should expect to see, so with this version of the code, we should expect to see head like increasing, and that's it. Tail is never going to change here because we disabled the code that actually reads in the packet data and then advances the tail pointer. So we're not doing that. But the hardware is going to be feeding us more and more data, and we should see head increment. That would be really interesting to see. Okay, now there is tail next undeclared. Okay, I'll just do it like this. Okay, right. Okay, so that. Wait, I'm just gonna. I was a bit confused because I didn't see the hex dump, so I thought something went wrong. But that's actually correct. We're never gonna see that like original. We're never gonna see this hex dump because we are no longer passing data back to user space. Okay, so we have this thing going. We got our ARP response, and then bam. And that was it. That happened. Let's look at what happened. That was interesting. It seems like look at all these unicast matches. It's, to me, that sort of means that something came in. Like a packet was trying to come in. But what is also extremely interesting is that head never changes. And that feels super wrong to me. I mean, we can actually look in the QEMU source, and it might be the case that it never. Okay, you know, I don't know. How would we search? I'm looking for RDT, RDH, RDH. TDT. RDT. RDH. See if IOVEC. So here's where they increment. Yeah, the head. So clearly they do this. Let me go back to my. What's my history here? I have. My vague memory of that part of networking tells me you need to announce your IP or answer to ARF. My guess is that QEMU tries hard to guess your IP to see if the package should reach the host. Okay, I'm thinking about that. Let's go. I'm gonna go back and copy some of the stuff from all the way up here when we were learning all about this stuff. These IP addresses are all from the perspective of being inside the virtual network. Firewall DHCP server. So that's the thing, that's like this ARP server thing that we see responding to the ARP message. Hello? Okay, so also what is interesting? Hello dump receive IOV. Oh shit. Dump receive IOV. Okay, this is the function that dumps the PCAP. And we are not seeing that. We see that happen right here. And that's what goes into the PCAP. But then we just never see that again. Okay, I think I was getting kind of close though. real interesting point here is to see where RDH is changed. Yeah. So it seems like this function receive IOV. I'm just going to add a print here. Oh, shit. Okay. So I'm putting just a print in Kimu. I believe this is just the function that gets called when data is coming in for the hardware to receive. Yeah, let me try this. Hopefully the build works. I think that worked. This weird Kimu unsigned thing, but then I have my symlink. Since there are 4 more ARP messages logged, maybe it can be seen in Wireshark. Yeah, I don't know because okay, here it is. Well, we could rerun it again just to make sure. In order to see something in Wireshark, we need to see these hello dump lines. And that these 2 lines are, so these are my Kimu prints, and it's what produces the lines in Kimu. Yeah. AsmCube, good question. What is a size T data type? It's not a dumb question. It's a very... I remember being super confused by this with C programming myself because it's sort of like a weird type. Size T is an unsigned type that is the maximum unsized type that the hardware supports, basically. So if you're on 32-bit, it's going to be a 32-bit unsigned. If you're on 64-bit, it's going to be a 64-bit unsigned number. And these are often used for length parameters. And that's kind of because the C and C++ standard uses them. Unsigned integer type returned by the size of operator. Okay. Yeah. Yes. Let's run this again with the new Kimu. Hello, receive IOV. Okay, let's run this. Bam. Okay, maybe I should add my panic back. Wait, no, actually no. This is just doing that thing where it loops. So we do see hello receive IOV. So that function does get called, but head doesn't change. So now we can look into why. Incrementing RDH. Kimu. Shit. Yeah, so Dang, has it already been another 20 minutes? All right. Stand up and stretch. Palm tree break. Be right back. Okay, I think we are making some progress. So here's the part where it should increment RDH. Yeah. So RDH, so SM cube, RDH is not an assembly register. This is a register on the network interface card. Basically what it is kind of just like a hardware variable that is in the NIC. So this is not assembly though. And so I'm putting this print, because here's where RDH is incremented, specifically right here. We are never seeing head be incremented. It seems to always be 1. If I'm doing this correctly, so the way I'm reading RDH is I'm doing this, this like read 32 thing. And my guess is that we are not going to see this line. Let's see what happens. Bam. And then this thing. So I think oh shit, I need to recompile Kimu. Okay, let's try it one more time. Incrementing RDH, so that was the first time we saw it, and then bam. Whoa. Whoa, now that is interesting. Check this out. This incrementing RDH. All right, later, ASM cube. So check this out. We are actually seeing this incrementing RDH thing quite a lot at all the places we should see it. So this suggests that my printing is wrong. So how does my printing work? I'm pretty sure I'm reading the correct place. I'm reading, let's really get down to the receive descriptor head. Right, this is what we're talking about. This is RDH. It's at hex 2810, 2810. So yeah. It's after a reset and before enabling. Reading the head to determine which buffers are finished is not reliable. So yeah, so there's not that much to this, but it's interesting that it seems to like not. It like weirdly, something seems out of sync between the two. So on the driver side, we are, what's read 32 look like? I thought this was pretty simple. It's just adding the offset to the base. and dereferencing it. It's not really that complicated. So that's what gave me some confidence that I was doing this right. How do I start learning low-level things? Yeah, I have a couple recommendations. Dev and Chill. They're not like amazing, but I've just like this list of courses and other stuff that I've collected. If the chatbot works, okay. So odd. Okay, let's add more debug prints on here. Yeah, Nanobyte is pretty awesome. Okay, so now we're printing out the value of Kimu of RDH as Kimu sees it. Right, so this thing is going, increment RDH, and bam. Check that out. That is so interesting. Kimu RDH is saying it's like incrementing something. But okay, I'm also gonna do something else here. I do need to kind of get ready to get going pretty soon, but I'm in this just kind of debugging loop. I'm going to iterate over all of the descriptors, and I'm just going to print out some info about them. Equals get rx. No, it's just going to be grx descriptors at I, right? And then we're just going to yeah. Descriptor, and then we're going to print dd. And then I'm just going to do risk status and dd. Shit. Stat dd. That is the minimally the information. So I'm just on every like tick cycle, I'm dumping out the state of the head and tail. I'm also dumping out the state of all of the descriptors dd bits, and we'll be able to observe how they change as the different packets come in. Yeah, let's do this. Okay, and bam, right? I think that was it. So let's take a look at what we see here. It's a little bit, unfortunately, it's a little bit verbose. Maybe I can improve that by moving this all onto one line. Okay. And maybe I can also just move this onto one line also. Head, tail, right? Okay, ready, fire. So what happened here? So we had an initial state, 0 and 7. Everything was zeroed out. The ARP response came back. So that's a legitimate packet, right? So head points here now, and we see a DD bit set for 0. And that is now the steady state. And then what? And then I have shot off the UDP packet and it claimed to have incremented RDH, but nothing changed here in terms of the state of anything. So we had this one happened once, happened twice, happened 3 times, 4 times, 5 times. Nothing changed with the state of the head or tail or any of the DD bits. This is really interesting. Kimu is incrementing RDH on its side. We cannot observe this on the OS side. Furthermore, none of the DD bits seem to be changing, as these 5 or so packets seem to arrive. Super odd. Seems like RDH remains fixed. Super interesting. Something seems kind of wrong, but it's just, I mean, many things seem very wrong, but it's super odd that RDH on the Kimu side actually does change while we are trying to read it. Oh, wait a sec, guys, I think I know. I think I know what's going on, actually. This is something I never really understood, but it has to do with this part of the output. Let's take a look. So here, this is the output from the very early stage of like boot up, where the OS scans the PCI bus and discovers the like network controllers. And what I never understood is why there are 4 of them. And I think that matters here. Oh, I think I totally get it now. Because so we've been using like the driver like attaches to one of these NICs, and that's the code we're modifying. I believe actually every time you port forward, it actually creates a new virtual NIC. And so what I think is happening is when we send So I don't really know, but I think what might be happening is there's actually 4 NICs. Currently, our driver is only paying attention to one of them, and when we send data through the port forwarding thing, it's getting sent to a different NIC, which is being completely left alone. And I wonder if this would explain some things. So right now we have some global buffers. So here's what happens in E1000 init. No. E1000 attach. Mapped blah 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 base. This thing gets printed 4 times. But we only have one. We end up calling E1000 init 4 times, I think. Which is like could kind of work, but we only have one global driver object, and it actually gets overwritten. That's interesting. Yeah, this is weird, but yeah, we have 4 NICs here. So let me test my theory. Let me go into the make file and comment out all of these port forwarding things. Now let's take a look at what the output looks like. All right, we don't even need to go further. Look at this. So this is kind of different. We have the big PCI output for a bunch of these random other devices. And then look on the left side, we have 4 different log lines of a NIC being instantiated. On the right side, we only have one of these lines. So to me, that smells like, yeah, the source of this problem. Each of these port forwarding things seems like it creates a new virtual NIC. I'm going to ask ChatGPT about that. It seems like Kimu is creating a new virtual NIC device for each port forward argument I provide. Is this correct? First time here, amazing keywords. Let's quickly compare and copy along, easily selecting and commenting code. Thank you. I kind of suck at Vim, actually. I'm not really that good. I fumble a lot. Appreciate it. So each implicitly creates a new device with its own virtual NIC, virtual MAC address, and separate user mode stack. Holy shit. Yeah. Instead, if you want a single network interface with multiple port forwards, do not use multiple NIC options. Instead, consolidate all port forwards into a single net. Oh my god, thank you. This is exactly what I need. Let's try it. So, net dev, user ID, net 0, blah, 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 blah. So Mikhail, you were right. It was a bad Kimu argument situation. Let's run it. So what do we see? So, okay, so I'm just gonna stop it. We already we see one print, which is perfect. So, I mean, I think that was the source of a lot of our problems. So now we can do the netcat. And did something happen? No, I don't think anything happened. Okay, so nothing is happening anymore. Oh, but it's 1, 2, 3, 4, 5 now. Okay, it changed back. So 1, 2, 3, 4, 5, and then bam. Check that out. Okay. Oh shit. Oh. Why is this not exiting? Okay. Look at that. That looks great. A bunch of data came in, and furthermore, it even matched the MAC address. And check it out, our head thing is now consistent with RDH. It still is super odd that the DD bits don't seem but changing, but check it out, the dump thing is now active, so we can check out in Wiresharp what it looks like, and we can, I don't know, we can like see some stuff. I'm just gonna kill the palm tree, and here we go, we can see our hello guest. So now let's, I need to go in like a minute, but we can come back here, and shit, we can put the assert back, I think, and we can comment out this thing, which I think basically returns the state of things to how we want it. So then now I can try to run this thing, waiting for packets, and let's, moment of truth. Something happened, but not exactly what I wanted. So a bunch of stuff happened, but it seems like the, oh wait, it seems like the driver, dang. No data, received a buffer. Six. And it's something to do with the DD bits, okay. We're not exactly seeing it, but we are definitely on track to finishing this. So yeah, we'll do this later. So I got to end the stream now, but thank you very much for joining. I have a Discord link which I will post. Please like, comment, and subscribe to my channel if you dig what I'm doing here. And I'll see you next time. Right. Peace.